Okay, so for our final chapter here, we're going to be looking at correlation and regression with scatter plots. So we're going to be starting out here, looking at how do you construct a scatter plot. We'll look at doing it by hand, we'll look at the calculator and Excel. Computing correlation coefficient, which is a very intense calculation, but we're going to look at ways to electronically make that easier. And then interpreting the correlation coefficient, what does it mean? Then looking at a very quick side note, but very important, of correlation and causation. So let's look at constructing scatter plots. So what scatter plots are, what we're dealing with correlation is we're dealing with one set of items, but two measurable variables about them and looking at the relationship. For example, if we're looking at humans, people, we could look at their height and their weight. Normally, the taller a person gets, the more they're going to weigh. So there's two measurable variables about the same subject that might have a relationship between them. So we take those and we make a single dot for each subject, but we put one variable on a horizontal axis and the other variable on a vertical axis. So here we have real estate agent wants to study the relationship between the size of a house, I'm assuming in square feet, and its selling price. Is it reasonable? It is reasonable to expect the bigger the house is, the more it's going to sell for. So specifically, larger houses will have a higher selling price. So we're going to put this on a scatter plot and see if we can see that relationship. So we're going to gather some data. Here we have several houses. And you can see this is their square footage. So this house was 2,521 square feet, and it sold for $400,000. And on down the list, we have 1, 2, 3, 4, 5, 6, 7, 8 houses here that have sold. So for our scatter plot, we put the size on the bottom and the price on the horizontal axis on the left side. This is the independent variable down here, because the size, you can make a house whatever size you want to. But once you have the size, that variable affects the price. So this price here is affected by the independent variable. So this is called the dependent variable on the left side here. So on bottom, independent. Get my pen to work here. There we go. Independent. Like I said, we can vary that however we want to. We can make the house bigger or smaller within reason. And this is dependent because once the size of the house has been determined, the price is affected by that size. So you can't make the house, I mean, you can make it whatever price you want it, but you usually do that by adjusting the size. So if we were going to enter this in the calculator, we're going to go to Stats and Edit here. I'm going to clear out my lists. Okay, so we're going to enter the data here. I should go back to the table here so I enter the data in. So 25, 21, 25, 55, 2735, 2846, 3028, 3049, 3198, and 3198. So those two are the same size. Prices 400,000, 426, 428, 435, 469, 475, 488, and 455. So we've got those all entered. We're going to exit out of there. Second quit. Oops. So here we are. So now what we're going to do is we're going to go to the stats on the calculator. Oops, that's not what I was looking for. So we're going to go up here in the stat plot. The second stat plot. And we're going to turn the first one is usually turned on, but if not, you'd arrow over. You'd select the first one, and you'd arrow over to turn it on. It's already turned on here. So now we're going to come down here and we'll select the type. That first type is a scatter plot, so I'm going to select that. The X variable, X list, is in list 1. The Y list, the Y variable, is in list 2. Select what we want to mark it with. We're going to use the bigger dot. And then to get out of there, I'm going to either hit graph, trace, or zoom. I'm going to hit zoom, and then we're going to select standard, which is option number 9. Or zoom stat, I should say, not standard. Zoom stat for option number 9. So it gives us that statistical zoom for a scatter plot. And you can see there's our scatter plot, just like pictured here. If I wanted to do this in Excel, go back up to my table here. So easiest in Excel if you make the list vertically. So we're going to do square feet and price. So 25.21, 25.55, 27.35, 28.46, 30.28, 30.49, 31.98, 31.98, 400,000, 426, 428, 435, 469, 475, 488, 455. And it's really simple. We highlight both columns, including the title. We go up to insert, and we can go to Scatterplot. And we'll just select the first one as a Scatterplot. And there it is. You can see it puts the price is listed on top. That's not what we want for the title, so it didn't label our axes very well here. I'm going to get rid of this as my key. I'm going to get rid of that. I am going to format this axis. I got to change it around. I want to set the minimum number. Nothing below 2,400, it looks like. So I'm going to set my minimum to a fixed 2,400. And so that changes this axis here, so the data stays on the plot. Now on the left side, I'm going to do the same thing. I'm going to format that axis. I'm going to set that minimum, looks like about 300. Actually, even 350. So now we get a little bit more definition that way. I could even come back and probably change it to like 390 if I wanted to. Let's do that. Let's go 380, actually. It'll be a nice spread. So it gets the points spread out so you can see they're spread across the table. We could also look here at displaying, let's see here. Okay, so then from there we'll be able to add in all of our correlation coefficients and stuff like that. So let's go back now to our tables here. So we can construct them with the calculator, we can do them by hand, we can do them with Excel. Now, things that we notice here, there's something called increasing and decreasing, or positive association and negative association. In a positive association, as the numbers on the independent axis get larger, the numbers on the dependent axis get larger. And vice versa. If the numbers on the independent axis get smaller, the numbers on the dependent axis get smaller. So what happens, we get lines that slope as we go from left to right, they slope up, or positive slope if you're thinking algebraically. So we get a scatter plot that looks like that. A negative association is just the opposite. As the values of the independent variable get larger, the values of the dependent variable get smaller. So we have that line that slopes down like that. So we have positive association between variables, and we can have a negative association. Okay, so let's compute the correlation coefficient. This is actually a pretty intense calculation, so we almost always use technology. What it is involves us for each variable, we find x bar, the mean of all the x values. So in this case, that'd be the mean of the square footages. Y bar, which is the mean of all the y values. And then Sx is actually the standard deviation of the x values, and Sy is the standard deviation of the y values. So we have to apply it into this formula. For each value of x, we do the value minus the mean for x divided by the standard deviation, with its matching value for y, minus the mean for the y is divided by the standard deviation. We add all those values up, and it's 1 over n minus 1. There were 8 numbers here, so n is 8. N minus 1 would be 7. If I wanted to do that in Excel, I'm going to copy and paste this table down here so I can work with it. So let's do the mean and standard deviation here. I'll find the average of that set of data, the mean of that set of data, the mean of that set, standard deviation for each set. So there we have them. And now for each value here, we're going to compute equals this value minus its mean. Oops, I got to put it in parentheses here. Minus the mean divided by the standard deviation times this value. Parentheses again. So this value minus its mean divided by its standard deviation. Now I'm going to go back in here and I'm going to put some dollar signs in here so that it doesn't scroll down. So we're going to pull that on down there. We add those up. So we get 6.3. Now we're going to divide by, well, we'd multiply by 1 over 7. Remember, that's n minus 1. 8 is n, so it's 8 minus 1 is what we're dividing by. So we get a 0.90059 correlation coefficient here, according to that formula. They want to discuss what that correlation coefficient means here a little bit before they go about calculating it. The correlation coefficient should always be between -1 and +1. If it's at 0, that means there's no correlation. The further it is away from 0, the stronger the correlation is. If it's a negative value, that means it's that negative association, or the independent variable gets bigger, the dependent variable gets smaller. If it's closer to a +1, then it's in a positive correlation. As the independent variable gets larger, the dependent variable gets larger as well. So here's our data set again. They're starting out with that calculation as we did here. You got x bar, y bar, standard deviation of x, the standard deviation of y, started in the formulas. Here's their table, just like what I did. They were getting 0.9005, which is what we had, 0.9005. So what that correlation means, since that correlation is positive, first of all, it means it's a positive association. As that independent variable gets larger, the dependent variable gets larger as well. So in other words, if we're looking at our graph, we're expecting this to have a positive slope like that, sloping up. It's fairly close to 1, so that's a relatively strong correlation. Now, how strong it is depends on the number of data points. And for this course, we're really not going to look at testing that strength. There are tests you can do for strength, and there are tables you can look up. If this were just a little bit more rigorous course, you could look up in the table that would say, okay, for n equals 8, because there's 8 data points in here, what is considered a strong value, a correlation coefficient? The fewer data points there are, the easier it is for that correlation coefficient to be strong. If there was only like 3 or 4 points, it'd be really easy for that to be close to a positive 1. You get up to 8 or 10 points, now they have to have a decent relationship in order to get that correlation coefficient up to that 0.9 or close to 1. If you get up to 30 points, now they really have to lie close to a line to get a strong correlation coefficient like that. So what that value of that correlation coefficient needs to be to show strength, as I said, depends on n. It depends on the number of points we have, number of ordered pairs we have. So let's interpret that correlation coefficient. As we were saying, if it's positive, it's a positive association. In other words, it slopes up across our graph. If it's negative, it's a negative association, meaning it slopes down. If it's 0, that means there's very weak linear association, or it's not a linear relationship. So they're just going to be scattered across the graph, and it may not be a linear situation, a linear relationship between the variables. If it's close to 1, that means it's strong linear. If it's close to negative 1, that means it's strong linear, but in that negative association. Does not mean the slope, by the way. Whether this looks like this or like this, those are both positive associations, and they can both have a correlation close to 1. So don't confuse slope to correlation. Correlation just means how close those points lie to that line, regardless of the slope. Both of these are positive slopes, so they're both going to be positive associations. And if the points lie perfectly on those lines, both of them would have a correlation of positive 1. Same in the negative. This is a negative slope. This is a negative slope. But the correlation is how close the points are to those lines. So to get close to a negative 1, you just have to have the points close to the line. It doesn't have to have a strong negative slope or weak negative slope, or small negative slope, I should say. It's how close they are to that negatively sloping line, regardless of how steep the slope is. So if r equals 1, that means they lie exactly on that line. It's a perfect positive association. And the same if r equals negative 1, they're exactly on the line. It's a perfect negative association. Almost never do we run into that unless the data was produced by a formula. If they're not linear related, then the correlation coefficient does not provide any reliable description. So then we can't proceed to that regression equation that we're going to talk about in the next section. The correlation coefficient is not resistant. We talked about resistance with the mean and the median. We talked about how the mean is not resistant. An outlier can drastically affect the mean, but it won't affect the median that much. Well, so the median is resistant because it's not hugely affected by those outliers. The correlation coefficient is not resistant. And one outlier can throw that correlation coefficient way off. And usually that outlier will make that correlation coefficient be really small. So make it deceivingly small. So correlation is not causation. This is a discussion that we have to have. Just because the correlation coefficient is strong, like close to 1. Now let's say we have our points here, and they look like they're falling really close to a straight line. There's our points. That's pretty close to a straight line. That doesn't mean the two variables are causation. It might be that both of them are caused by the same third factor. For example, maybe weight and vocabulary, or weight and score on a test. Well, as you get older, you tend to weigh more, but also as you get older, you tend to learn more, and you score better, higher scores on tests, on same tests. So here we're looking at a group of elementary school children took a vocabulary test, and it turned out that children with larger shoe sizes tend to get higher scores on the test. So again, there's a case where either one of two things happened. Either the older students happen to have larger feet, and therefore they'd larger feet, and they're older, they'd have a larger vocabulary. So both of those items, both of those changes in those variables were caused by the same single cause of age. The shoe size did not affect the vocabulary or the other way around, but they were both affected by a common cause. Or it just happened to be a coincidence that the shoe size happened to go up as the vocabulary went up, and there's no real relationship at all. But it definitely does not mean that as a person's feet grow, their vocabulary grow. So the fact that the shoe size and vocabulary are correlated does not mean that one variable caused the other. So the calculator will calculate correlation, and we'll look at it when we do our regression line. We'll actually do correlation on Excel as well when we get to that point. So we looked at how we construct scatter plots, and we looked at calculating the correlation coefficient and interpreting it, and also that warning against assuming causation. So now let's move on to looking at the least squares regression line. So once we plot these values, we want to be able to see if we can find an equation for a line that goes through them. Now, again, that correlation coefficient tells us if there's a strong enough relation that we can bother. I mean, if the correlation coefficient is too small, the regression line really doesn't mean anything because it's not a good estimate for the data. So we're going to compute the least squares regression line, use that to predict stuff about the data and predict values for other values. And then we're going to look at those predicted values and interpret the slope and the y-intercept of that regression line. So let's look at computing it. Just like the correlation coefficient, this is a rather intense calculation if we were to do it by hand. What it is we're looking at taking the data points and drawing a line such that the distance between the data point and the line is minimized. Here, this would be a bad regression over here because you can see the points are a long ways away from the line. Here, this is a decent regression line because the points are really close to the line. So least squares is saying we're going to draw on that line so it minimizes the total of all those distances. Our equation is going to take on the form of y hat, which is the predicted value of y from the equation, is equal to b0 plus b1 times x. Now b1 is easier to calculate. b1 is found by taking our regression, or our correlation coefficient, times the standard deviation of the y values divided by the standard deviation of the x values. So if we look back at this example here, we had the standard deviation of the y values and standard deviation of the x values, and here's r. So b1 would equal r times the standard deviation of the x divided by the standard deviation of the y, 0.8176. Oops, I got that backwards. So it'd be standard deviation of the y over the standard deviation of the x. Let me change that. So standard deviation of the y divided by standard deviation of the x. That's going to change it some. So I'm getting 0.099. Let's see how that works out here. This is kind of equivalent to the slope. So if we're looking at an algebraic line, that's describing how steep the line is. So we're looking at the variable we want to predict. In this case, the selling price is the outcome variable, or response variable is what I'm used to calling it. That's the dependent variable. And the variable that we're given is called the explanatory variable, or the predictor variable, and that is the square footage. The price is the response variable, the square footage is the predictor. We're trying to use the predictor, use the square footage to predict the response. That's the price. Okay, so they did the calculation for our set of data here. They found R, they found SY and SX, and they plugged them in and they get the same value we just got, 0.099, 0.0992. So they plug those values into the formula. Now, once we know that, then we use X bar and Y bar to find B0. So B0 is found, if we actually went back to this equation here, we put in Y bar and X bar here. This is the mean of the Y values and the mean of the X values. And we put in our value that we just found for B1 and we calculate B0. And that's what this formula here is just solving that for B0. So it's Y bar minus B1 times X bar. So Y bar was 447 minus B1 we just found to be 0.099. And X bar was the 2891.25. Gives us 160.193. So our regression equation here becomes 160.193 plus 0.0992. Now if I want to do this on the calculator, first thing we have to do is we have to hit the catalog button down here. So second and catalog down here. We've got to arrow down to diagnostics. If you're just bought your calculator, the factory settings would be for diagnostics to be off. Or if you've had to reset your memory because you've had any problems, your diagnostics will go to off. So we're just going to go ahead and do this to guarantee our diagnostics are set on. So we selected diagnostics on. We're going to hit enter. And you have to hit enter again to execute that function. So now it's done. Now what that means is when we do a linear regression, it's going to give us the correlation coefficients and stuff like that. So we can clear out here. And now we're going to go ahead and we're going to go to calc on the calculator. So we're going to stats and calc. You see linreg AX plus B. So I hit enter. I hit enter again. Now we had to have, I already had the variables in those lists, remember. Now we had list 1 was the areas and list 2 was the prices. And you have to have that. You have to have your independent variable or your predictor variable in the L1 and your response variable or dependent variable in L2. And here you can see A, which was our B0, is 0.099. B, which is our B1, was 160.19. And this is our correlation coefficient. R is 0.9005. So that was our correlation coefficient. R squared up here is called the coefficient of determination. And this textbook doesn't stress it a whole lot, but that actually can be interpreted as a percent. 0.811 is 81.1%. And what that is saying is 81.1% of the variation in the Y variable or independent variable can be predicted by the values of the X variable and the regression equation. So that's really a good measure of how strong this is. This is 80% of the independent variable or the dependent variables is being predicted by the equation and the dependent variable. Okay, so we've got our information there, exactly what we had found on our calculator right here. So next, if we use the least squares regression line to make those predictions, well, I'm going to jump to Excel here quick, and I want to go back to my graph here. This is my data. If I click on one of those points and I select Add Trend Line, select Linear here, I want to display the equation and I want to display R squared on the chart. Hit OK. And what it gives me here is the equation 0.0992, which was our B0, and the 1 times X plus the 160.19 was our B1, so those are the same. Now it gives us R squared here instead of R. So in order to find R, we have to do the square root of that R squared. So 0.8111, and that's that 0.9006. There's a little bit of a round off error there. We had 0.90059. So that, because it only goes to 4 digits, when we square root it, there's going to be a little bit of a round off error. But that is within acceptable parameters there. So let's use this equation to predict. If we use the least squares equation to predict the values of an outcome variable if we're given the values of the explanatory variable. In other words, we're going to find the value of y hat for a given value of x. So we've got the least squares equation. Predict what the price would be. Predict the selling price for a house that's 2,800 feet. So 2,800 goes in for x. So here's our equation. 2,800 goes in here for x. Now we just multiply out the equation, or we do the order of operations on the equation. Do the 0.0992 times 2,800, and then we add the 160.1939, sorry. We get 438,000 as the predicted value. The least squares regression line goes through the point of averages. So the average value of x squared, or of x, and the average value, the mean value of y as well. It should go through that point. So that is the average of all the x values, the mean of all the x values, and the mean of all the y values. Okay, so interpret the predicted values and the slope and all that stuff. So we use that least squares regression. If we want to do a house with 3,000 square feet, we predict its value, put 3,000 for x, just like we did up above for 2,800. We'd predict its value to be 457.8 thousand. Now we're saying we're not saying that's what the house should sell for. We're saying we estimate based on the regression relationship that a 3,000 square foot house would sell for $457.8 thousand, or 457,800. The y-intercept here is saying that a house with 0 square feet should sell for 160 bucks. That's basically what that's accounting for, is the basic costs of preparing the lot and the water and sewer hookups and stuff like that. There's costs there that you're going to have in the house that doesn't add to the size. Now, obviously, it costs more than 160 bucks. Oh, actually, 160,000 in this case is not the cost of putting up the sewer and water, but it's, that'd be the cost of your sewer, water, your lot, and everything else. So in this area, rather expensive lots by the looks of it. But a house of 0 square feet, so everything before you can even start building the house, you're going to have $160,000 in it. Then the slope here of 0.0992 is saying every square foot you add to the house is going to add, on average, again, all these are on average. Every square foot is going to add on average 0.09. Now remember, this is in thousands again, so it's going to add $99 to the value of the house, every square foot. So we have computed the least squares regression line, we have used the least squares regression to make predictions, and we interpreted the predicted values and the slopes and the y-intercepts. So that is it for this unit. If you have any questions, please let me know, and I'll get back to you as soon as I can. Otherwise, have a great week.